today in this video we're going to be looking at the integral from 0 to 1 of x to the power of x. This is commonly referred to as Bernoulli's integral. We also differentiated x to the power of x in the last videos, and also in the video before that even, we looked at the integral from 0 to 1 of x to the power of negative x. And so if you have seen that video, I would recommend pausing now and having a go at solving this integral, as it requires a very similar method. So yes, go ahead. I'll give you a second. Right, now, like last time, x to the power of x, well, that isn't really a nice form of an integrand, because we can't apply any of our standard rules to this. We can't apply integration by parts. We can't apply a use substitution here just yet. And also we can't do a series expansion here just yet. So there isn't much we can actually do here. The main idea is we've got x to the power of x, and we want to be able to rewrite this in a more useful form. So that's what we're going to aim to do. And the way we're going to do that is, so we've got the integral from 0 to 1. We're going to write this as e to the power of ln x to the power of x, like this. E and ln, they cancel out. And so we've still got the integral of x to the power of x. We've just written it slightly differently. Okay, now using the laws of logs, we can bring this x in the power of the ln out to the front of the ln. Okay, so that becomes the integral from 0 to 1 of e to the power of x ln of x dx, like so. Okay, well, where can we go from here? Well, like last time, I want you to be able to recall the series expansion for e to the x. So we've previously said that e to the x can be written as the sum from n is 0, and I'm going to use n this time because I used k before and I was severely told off for my for my handwriting in the last video. Anyway, so we've got the sum from n is 0 to infinity of x to the power of n over n factorial. That's what e to the x can be written as. I believe this is the Maclaurin expansion, if that's how you pronounce his name. I've never really been able to pronounce that name correctly, I don't think. Okay, so let's see how that actually relates to the integral that we've got here. So we've got the integral of e to the power of x ln x, and we know the series expansion for e to the x. Well, hopefully you can see the relationship we've got here between these two things, and that's the fact that x ln x we can place in to sort of this x here, basically. And so what I mean by that, and what this is going to become, e to the power of x ln x can be written as the sum from n is 0 up to infinity of, now replacing this x here, because we are replacing this x, of x ln x all to the power of n over n factorial dx. So hopefully you can see what has happened here. We've replaced the x in the series expansion for e to the x with x ln x. We are allowed to do that. That's perfectly okay. Okay, so where do we go from here? Well, it would be useful if we could interchange the integral and the sum. Now, last time I skipped this step and I just did it and didn't really justify my the reasoning for it. We're going to do that this time, okay? And the way we're going to do that is via the dominating convergence theorem. Okay, let's have a talk about the dominating convergence theorem. So it has to satisfy two conditions. First of all, our function, so our x ln x to the power of n over n factorial, it has to converge to x ln x as n gets bigger and bigger and bigger, aka as n approaches infinity, x ln x to the power of n over n factorial has to approach x ln x. Now, that is a job in itself, so have a go at proving that. We're just going to say that it does for now, and you can show a few ways that is the case. As n gets bigger, our and what we would call this is sort of f subscript n of x does approach f of x as n gets bigger and bigger and bigger. So that's the first condition it has to meet, which it does, so we can give that a tick. The second condition that it has to meet is that there's a function, let's call it g of x, that is always bigger than or equal to the absolute value of f subscript n of x. So what that means is the absolute value of n, f or subscript n of x is always going to be less than or equal to some function g of x. Now, this is called the dominating function. And it's also important that the function g of x, this dominating function, you have to be able to integrate it over the domain that we've set in the question. And that domain is from 0 to 1. So we need to find a function, which is called the dominating function, which satisfies this inequality and is integratable over the domain 0 to 1. I know, let's use the constant e, okay? Because the absolute value of x ln x to the power of n over n factorial is always going to be less than or equal to e for all x on our domain 0 to 1. Okay, so this works because the exponential series that we've got converges and each term becomes small enough to be bounded by that e. Okay, so that was, so we found g of x, but of course it has to be integratable over the domain 0, 1. So let's check that. Can e, the function e, be integratable or be integrated over 0 to 1, over that domain? Well, e is just a constant, it's just a number. And so when we integrate it, we get e times x from 0 to 1. And substituting in 1 and 0, we just get e as our answer. So the integral from 0 to 1 of e with respect to x is just e. Now, e is a finite number. It is less than infinity. Of course it is. And so it works. It can be integrated. Okay, so we have just shown these two conditions in the dominated convergence theorem. We have just shown them both to be true. Great. That means that we are allowed to switch around the integral and the sum. So in doing that, we get the sum now from n is 0 to infinity of the integrals from 0 to 1 of x ln x to the power of n over n factorial dx. Now, our integral here is with respect to x. So when we've got this n factorial here, well, that's got nothing to do with our integral. That is just going to be a constant. It doesn't have an x involved in it, so it's just a constant. We can move that to the outside completely fine. Let's go ahead and distribute that power of n here into our brackets. Okay, now we have got this integral to solve here. Now, there is a nice way that you can solve this integral via infinitely many iterations of integration by parts. However, we're going to be using the gamma function here. So if we recall the gamma function, this is a fascinating function, the gamma function. It was featured last time with x to the power of negative x. And if you haven't seen the gamma function before, I would definitely recommend reading up about it. So that's what we're going to try and use to solve our integral here. The integral from 0 to 1 of x to the power of n times ln of x to the power of n. Now the motivation for doing this is, hopefully you can see a few parallels. We've got this x to the power of n here, and in the gamma function we've got this t to the power of n here. Not only that, but in the gamma function we've got some sort of exponential thing going on, and in our function we've got this sort of ln thing going on, this natural log here. And those two things are obviously very closely related. So I'm wondering if we can do a substitution to get from one to the other, to get from our integral to the gamma function, because if we can do that, we know the result of the gamma function. So we're going to make a substitution here. Now the substitution that we're going to make is the substitution u equals negative ln of x. Now the reason I've chosen negative ln of x will become apparent in just a moment. So differentiating this, we get that du is equal to negative 1 over x dx. Also from this, if u is equal to negative ln of x, this implies that x is equal to e to the power of negative u. So hopefully you can see we're almost already getting to the gamma function with just the things that we're creating here. Let's now deal with the limits as well. Okay, so we've got the limits to deal with, 0 and 1. So when x is 0, well, what's u going to be? Well, when x is 0, we've got negative ln of x. So negative ln of 0, well, that is negative infinity. So u is negative infinity. And when x is equal to 1, we have got negative ln of 1, which is just 0. So we say u is equal to 0. Okay, so substituting in everything that we have just done into our integral, we can say that we've now got the sum from n is 0 up to infinity of 1 over n factorial times the integral. Now our limits are now negative infinity and 0. X to the power of n, well, what can we change that to? Well, we know what x is. X is e to the power of negative u. So we've got e to the power of negative u to the power of n, like so. And then we've got this ln of x right here, and we can change that to negative u. So we've got times negative u, and that's also to the power of n. And then we've got this dx to sort out. Well, we know what dx is from this. So from this, we can say that dx is equal to, so if we times up by the x and move the negative across, we get negative x times du. And what did we say x was? We said x was e to the power of negative u. So this is negative e to the power of negative u du. That's what dx is. So let's substitute that in as well. So we've got negative e to the power of negative u times du. There we go. Let's tidy up a bit because it's not tidy in the slightest. Now the first thing I notice is that we've got this negative here. Now this negative can be used to flip the bounds of this integral right here. I have also just noticed that this should not be negative infinity. It should be positive infinity. Sorry about that, because our substitution was negative ln of x, so it should be negative ln of x. So it should just be infinity. So let's get rid of that. There we go. Anyway, yeah, so we can use this negative sign to flip the bounds of our integral. So let's do that. Combining the e to the power of negative u to the power of n and this e to the power of negative u right here, we can rewrite this as the sum from n is 0 to infinity of 1 over n factorial times the integral from 0 to infinity of e to the power of negative u to the power of n plus 1, and then negative u to the power of n du. I'm going to take this -1 that we've got here to the power of n, bring that out of the front, times by the integral from 0 to infinity of e to the power of, we've got n plus 1 times u times u to the power of n du. And I hope you can see this is getting extremely close to the gamma function. Okay, so we've got one more substitution to do to get it into the form of the gamma function. And we've used u and we've got an n, so I'm going to use the variable t here. So we're going to say let t equal, and we are going to replace this now. So n plus 1 times u. So that means that dt is equal to n plus 1, like that, times du. And yeah, that's everything. The limits stay the same. They stay 0 and infinity. So now we've got the sum from n is 0 up to infinity of -1 to the power of n over n factorial times the integral from 0 to infinity of, so we're going to have e to the power of -t. What do we replace the u with? Well, we need to rearrange this for u. So if t is n plus 1 times u, then that means that u is equal to t over n plus 1. Cool. So now we can change that. So instead of u to the power of n, we're actually going to have t over n plus 1 to the power of n. And then what was du? Well, this is du right here. So that's going to be dt over n plus 1, and that's by rearranging for du right here. Okay, tidying this up a bit, we get the sum from n is 0 up to infinity. That was an awful infinity sign. There we go, times, so we've got the sum from n is 0 up to infinity of -1 to the power of n over n factorial times the integral from 0 to infinity of e to the power of -t times by t to the power of n over, so we're going to have n plus 1 to the power of n, but then we're timesing it by n plus 1 again. So that's going to add 1 to the power. So we're going to have n plus 1 to the power of n plus 1 here, dt. Now, our integral is in respect to t. It's in the t world. And so we've got these n's here, which have nothing to do with the t world. They're in their own n world. And so we can bring them out to the front. They are just a constant. Now, hopefully, you can see here that this is the gamma function. Let me bring the gamma function down again. Where's it gone? Here it is. There's the gamma function. We know the result of this integral right here because this is the gamma function evaluated at n minus 1. And so this is, let me write it in formally, the gamma function of n minus 1, which is n factorial. So rewriting what we've got now, we've got the sum from n is 0 to infinity of -1 to the power of n over n factorial times 1 over n plus 1 to the power of n plus 1 times by the result of the integral, which is just n factorial. Now, hopefully you can see here that n factorial and this n factorial cancel out. And so we've got the sum from n is 0 up to infinity of -1 to the power of n over n plus 1 to the power of n plus 1. Now, last video, we just left it here in this form, and not too many of you were happy with that. It was what the question asked. However, I didn't make that very clear. So what we're actually going to do is we're just going to go ahead and see what we get from this sum now. Because I understand not getting a value as the answer is a bit disappointing. So let's go ahead and evaluate this a little bit. So when n is 0, we've got -1 to the power of 0. Now anything to the power of 0 just gives you, well, 1. So we're going to have 1 over, well, n plus 1 to the power of n plus 1, so 1 to the power of 1, 1. Okay, and then we're going to have negative 1 to the power of 1, which is going to give you negative 1, so that's just going to be a minus now. And then we've got, here we go, we've got 1 plus 1 to the power of 1 plus 1, which is going to be 2 to the power of 2, and it alternates like this. On forever, up to infinity. And this is approximately 0.783431 ... And you can verify this on Wolfram Alpha. So yes, a very fascinating integral. I would argue very hard to solve, but very exciting as well. It uses the gamma function. Anyway, I hope you have enjoyed today's video. We reached 1,600 subscribers at the time of recording this video, which is 600 more than we had the other day. So that is absolutely incredible. The channel is growing faster than ever, and I can't thank you enough for it. So yes, thanks for watching. Hope you enjoyed the video. Cheerio.